So first of all, I would like to thank the organizers for putting together this amazing conference and for inviting me to speak. I will talk about fermions, mostly in optical lattices. And generally, of course, we hope to learn from these cold gases the secrets that are hidden in all these strongly interacting Fermi systems that we find in nature. So it turns out with fermions, you cannot simply put them on a computer, switch on some program, and just get the result of the calculation and know what will happen. You can write down extremely simple Hamiltonians, as we will see, and find that it's extremely difficult to find even the ground state, not even to speak of excited states. So there are often even qualitative questions. What are the transport properties? Why are they linear with temperature instead of with the t squared, for example, for the resistivity of high temperature materials? And we cannot just answer them by going to a computer. So that's where hopefully cold gases can help out by providing controlled precision many-body experiments to really solve these many-body problems. So there are various ways that get you into strong interactions, and of course we have seen many of those. Feshbach resonances is one example, which if you just put a spin 1/2 Fermi gas near such a Feshbach resonance, you can explore the rich BEC-BCS crossover from a Bose-Einstein condensate of tightly bound molecules to a Bardeen-Cooper-Schrieffer state of long-range Cooper pairs. You can switch on a lattice, as we have also heard several times, and instead of using a Feshbach resonance, you simply quench the kinetic energy and therefore promote the importance of interactions. And that gets us into the Fermi Hubbard model, which will be the main topic of my talk. You could also switch on more complicated interactions, long-range dipole interactions. For example, we have seen the beautiful talks, for example, by Francesca Fellaino on modifying the Bose-Hubbard model by switching on dipolar interactions. This leads to rich physics, and also in the case of fermions, we expect new things to happen. So these are just a few examples. Let me give you the textbook Fermi gas that you find when you grow up and learn about quantum statistical mechanics. You put fermions in a box, you quantize the box, and find out, according to Pauli, you should only put one particle per energy state, and you fill this box up to the Fermi level. It turns out in cold gases, this was not how it went. We, of course, had an easier time trapping inhomogeneous Fermi gases in approximately harmonic boxes, harmonic traps, and we were very happy with that. Actually, it was also sometimes a crucial advantage for us to have this inhomogeneous density. But we have learned, most importantly from Zoran Hadžibabic's group in Cambridge, that you learn new things when you really go back to the textbook. It's actually funny that Fermi, 90 years ago, also started with a harmonic trap just because it was just easier for him to calculate in the harmonic trap. But then, of course, the textbook becomes rather the box potential. So here we create a box, put our fermions inside, and have a pretty nice homogeneous density. Now, this is not only to realize some textbook experiment, but actually there are states of matter that would simply not exist or cannot be found if your density is varying, like the full de Ferrier-Lakinov-Chinnikov phase. So we have an intrinsic motivation to go to the box to find new states of matter. And there is a wonderful way that we learned from our chairman how to actually give wonderful time of flight that corresponds to an infinite time of flight. You simply expand this gas into a harmonic potential in one direction here, and that gives you a momentum distribution from which you directly can get the occupation of each momentum state versus k. Well, that is the Fermi-Dirac distribution. You directly see the fact that fermions cannot be together in the same momentum state, so you see Pauli blocking, and you see the formation of the Fermi surface directly. And it's cute to note that 90 years ago, Fermi and then Dirac came up with this formula for the distribution of momentum states. In this box, we can find condensates where you perform what's called the rapid ramp experiment, trying to take, if you form some Cooper pairs, trying to glue them together into molecules, look at the momentum distribution of the molecules, and see whether you see a sharp peak in the momentum distribution. Now, it turns out, once you do that and you have a condensate, this condensate is so slow, it doesn't expand at all. So actually, it retains the shape of the original box. And so you see this rather nice flat profile of the condensate telling us we really have formed a homogeneous superfluid state here. Sometimes we also see vortices telling us this is indeed a superfluid state. You might be now a little bit saddened by the fact that we go to this homogeneous case, because you're like, you might remember that the trap was very useful to provide the equation of state of gases. So you could just climb up the hills, so to speak, of this trap, explore different densities at once, and look at the equation of state essentially from a single shot of the experiment. Signal to noise meant that you had to take 100 images of the experiment, but still the principle was nice. Now we have the box. How do you know what you have in this box? Well, you can get back to the old days, but only in one direction. You can have what I would call a harmonic box, where in one direction you have a harmonic potential, which again scans you through your phase diagram, and along the two other remaining directions, you are still flat. So that's the best of both worlds. You directly get the density as a function of position, which varies beautifully through this harmonic potential. You see the varying T over Tf, and you can immediately read off thermodynamic quantities. The pressure, for example, or more interestingly here, the compressibility of the gas. And let me zoom in the compressibility. For non-attracting Fermi gas, you beautifully see the saturation of compressibility, as you expect from the Pauli principle. At some point, you can no longer pack more atoms in there than given by the Pauli principle. In the center, interesting things happen in the polaronic phase, where I do have a mixture that I don't want to go into. We can, of course, do this for the balanced gas, the unitary Fermi gas, right at the Feshbach resonance, which is actually very difficult to calculate on computers already. Some calculations take months to run. We can get the equation of state in a couple of shots. These are 3 shots averaged, which show the sudden rise and fall of the compressibility, indicating the superfluid transition. So this is introducing you to the world of homogeneous Fermi gases. But now let's go on to a lattice. The simplest model that you can write down for interacting fermions is the Fermi Hubbard model. You have tunneling, and you have an interaction that is just on site. Atoms can only interact when they are at the same site. And it is believed that this model contains the essential features of high-temperature superconductors. I say believe because, again, one cannot solve for the full properties of this model, especially transport is also extremely difficult. It is not even clear what phases and how many are described by this model. This would be the famous phase diagram for high-temperature superconductors. Clearly, something here looks already different than what can be described by this model, especially the asymmetry that you see. There's a larger interferomagnetic phase here in the overdoped regime than in the underdoped regime, and different sizes of the superconducting dome, but the generic features might be captured by the Fermi Hubbard model. And of course, in cold atoms, we have a wonderful history trying to realize this Fermi Hubbard model in pristine fashion. It was already seen when you increase the interaction strength, the number of doublons, spin up and spin down on the same site, is strongly reduced because they just don't want to pay this price of the interaction energy, the repulsive interaction. So you see a reduction in the double occupancy in Tillman-Esslinger's experiment. And you also see a reduction in the compressibility of the gas. Once you have packed in so many atoms that you have one atom per side, you no longer can fill in more unless you overcome the energy gap U. The Fermi Hubbard model supports interferromagnetic correlations, as you have already learned in the morning, and beautiful experiments have been carried out in Tillman-Esslinger's group and in Randy Hewlett's group to directly observe these interferromagnetic correlations here in a beautiful Bragg experiment in Randy Hewlett's group at Rice. So now we have, of course, already heard in the morning that quantum gas microscopy is a wonderful tool to actually locally probe the system and see what happens. Kind of the complementary way to look at things other than momentum space. You want to really see what's happening locally, and it's ideally suited, of course, for lattice experiments. And of course, for a long time, people knew it would be wonderful to have these microscopes for Fermi gases, so that you can actually directly look at how nature solves the Fermi Hubbard model by looking at every single atom in a given realization of the system. So we set out to do that along with other groups. In our system, we have the atoms sit right below our vacuum window, which has turned into a hemispheric lens that boosts the numerical aperture to 0.9, so that we collect actually 20% of the photons that the atoms emit. So that's wonderful. Healthy collection efficiency. We use Raman sideband cooling that I don't have time to explain in detail. It's, of course, very well known from the Eintrap experiments, where you lower the vibrational quantum of your atom, first using a coherent drive. This needs 2 photons, actually, in cold atoms, neutral atoms. A 2-photon drive, lowering the vibration quantum by 1, and then an optical pumping photon makes sure that you end up back in the same spin state that you started with. This works beautifully. You can actually see in this image single atoms under the microscope. And we can, of course, verify that the resolution is sufficient to detect atoms on different lattice sites. So this is a nice 3x3 cutout of the lattice, where at the corners of the 3x3 lattice you have atoms. Let's look at the temperature after this cooling. It's actually interesting whether the atoms are still quite cold after you have imaged them. And it turns out, yes, they are. After this Raman sideband cooling, still above 70% of the atoms are still in the absolute ground state of each lattice site. So that's actually very nice. And if this could be pushed to even larger ground state populations, and actually we didn't even try to optimize for that, I do believe very interesting experiments become possible where you actually first know where they are and then you reshuffle them and play Maxwell's demons, so to speak. So now, since last year, there have been 6 quantum gas microscopes for fermions coming online for potassium-40 and for lithium-6. We have not yet run out of color schemes, so please add your experiment onto that slide. And now with that, we can try to get colder and explore the Fermi Hubbard model. As you have already learned, there's a metallic phase when there's still room to move. There's a Mott insulating phase when the atoms are filled in this half-filling case, so that there's no more room to simply tunnel. And if they wanted to tunnel, there is a repulsive interaction which forbids that between spin up and spin down. And there's, of course, also the band insulator when you simply fill the lowest band of the optical lattice completely with up and down. In a trap, this looks like that you have the band insulator in the center, where you have high densities, and outside maybe Mott insulating regimes. And in between, there would be metallic phases. So this is what both Markus Greiner's group and my group at MIT have seen under the microscope over the last year. Here you see Mott insulating, band insulating phases. Let me actually go in a little bit more detail. This is it looks hot, but it's actually not a hot phase. This is a very cold metal meaning that there's still room to move around. This is the Mott insulating phase where you have one atom per side, and this funny shaped picture tells you immediately there is a band insulator in the center. A band insulator has 2 atoms per side, so upon imaging, it turns out in our parity projected way to image these gases, we see no atom surviving. So 2 becomes 0, and that gives you a central region where there's simply no signal. We can, of course, perform azimuthal averaging again and plot this data as a function of radius. And again, this is starting to get into this equation of state business again, where you can now see again how the atoms climb up the hill of the confining potential and try to get the equation of state out of these shots of the experiment. Here we do the other way around. It turns out at our temperatures we still know the equation of state and can fit it to the data, and it works beautifully. We can also look at the variance, seeing that, for example, in the Mott insulating state, where you have 1 atom per side, you have a highly reduced fluctuation of this signal. And the entropy is for all these 3 cases rather low. It's 0.8 per particle. Low is, of course, a relative thing. In the superfluid Fermi gas that I showed before, in the bulk, we can reach entropies of 0.05 kb per particle. So there is still room to improve, of course. But one should say that this entropy in the Mott insulating phase is very close to log 2, roughly 0.7, where that would be just the entropy remaining of not knowing which spin state you have on a given lattice site. But you have already squeezed out all the charge entropy. You can, of course, very easily mess up the system by just waiting around and heating it up and seeing that indeed it obeys the equation of state at various temperatures. This is holding the system for up to 3 seconds, so that's a rather healthy lifetime, a slow heating in this lattice. And now let me actually try to understand more in detail what the signal is that you actually see here on the screen. As I said, parity imaging detects singly occupied sites only. So for fermions, you can actually write the signal as the local spin, if you want, n up minus n down, squared, because you don't know which spin it is, but you know if there's a single guy there, you get a signal. If there are no atoms, you get 0 signal. If there are 2 atoms of either spin, up minus down is 0, so you get again 0. So that's a nice direct correspondence of what we measure and an operator in quantum mechanics that expresses what we measure. So this is called the local moment. The local magnetic moment coming from the condensed matter world, where having a single guy there means, of course, that you have a magnetic moment sitting there. So it's a local magnetic moment. The average local magnetic moment, again, we have seen already versus radius. We can also ask, what's the fluctuation of this local magnetic moment? Maybe that gives us some other interesting thermodynamic property. No, unfortunately not. If you go through the math, the variance of this local moment is just given by the moment itself. So it does not give new information. It's just a binomial distribution, 0 and 1, and of course I cannot get more information out of that when I square it. 1 squared is still 1. Actually, the local moments are very useful for describing the Fermi Hubbard model. We can see that from the Hamiltonian, where I have added the grand canonical piece because I want to fix the chemical potential instead of the number. I can rewrite the interaction part, n up times n down, in terms of the local moment by just using the binomial formula. This thing is actually just the local moment. And this piece here is just the total density, which I can sneak into the chemical potential. So I can rewrite the Fermi Hubbard model in terms of local moments, in terms of the quantity that I directly measure in the microscope. So that is very nice. An image of our experiment directly gives us actually this potential energy term. And you can read off from this potential energy term that it's profitable for the system to form these local moments at low temperatures. So that's exactly what drives the system into this Mott insulating regime. We can plot the local moments versus temperature and see that, yes, we form this Mott insulator at low temperatures. Even at 0 temperature, we should not expect 100% local moment because we are not at infinite repulsion. There is still some tunneling going on even at 0 temperature. And that means if you take a snapshot, you will not always find an atom there, even in the Mott insulating phase. If you look somewhere else in the system, not in the half-filling case, but somewhere in the wings of the cloud, you start seeing, of course, different behavior where the local moments simply go away. The density simply has to go away as the temperature goes away from 0. So this happens when you look at a different chemical potential, which doesn't correspond to this so-called half-filling case. Now, what microscopes are really good for is looking at correlations. Because I have this beautiful image, it's a single realization of the Fermi Hubbard problem, and so I can ask, if I find a particle here, what is the probability that I find a signal on the neighboring side, for example, or 3 sides away, etc. What do we expect? Actually, at half-filling, we expect interferromagnetic spin correlations, as you have already seen in the morning. If you find a spin-up particle on one side, it is more likely that the neighboring side should be spin down than spin up. As you will learn, actually, this already happens for the non-interacting Fermi gas, curiously. It turns out what is even more interesting is going away from half-filling, because honestly, half-filling, we can put on a computer. We can solve for the complete phase as a function of phase diagram as a function of temperature at half-filling due to some beautiful particle-hole symmetry. But if you go away from half-filling, we are in the dark. And that's where we should find this interesting superconducting dome, for example, at low temperatures, and also a phase that people call strange metal. It's normal metal, but it's really a strange metal. Strange tells you they don't know what's going on. And the pseudo-gap phase, which also tells you they don't quite know what this gap actually is. It's pseudo. It's kind of not real. It doesn't make sense, or it's not typical. So in fact, in this regime, we don't know much. So it's very good to go away from half-filling and see what happens. There, actually, I would claim charge correlations should be more interesting to look at, or should be more dominant. You already have strong charge correlations, of course, for the low-filled Fermi gas. So we need to look at both, of course. And Hans-Christoph already introduced for me the G2 function, which is very nice now. If I know that a particle, a fermion, is at 0, what is the probability to find another like fermion a distance r away? You all know this from the statistical mechanics textbooks. There is a Polyhole that describes that not only can the fermions not be on top of each other, that would be called anti-bunching, but also there is a range given by the de Broglie wavelength, or at very low temperatures given by the interparticle spacing, where they don't want to be near each other. And then there are actually some Friedel oscillations, which are difficult to see and have not been seen in fact, in any experiment, I claim, in 2D. But as we just heard from Hans-Christoph, they have been seen in bosons in 1D in his beautiful experiments that he just described. For the Polyhole, there is no direct experimental observation. So you can look, of course, in time of flight, and then you see anti-bunching and the reduction of density fluctuations, but it hasn't been seen in situ. There were simply no microscopes. How does it look like in a lattice? Actually, it's rather similar. In a lattice, instead of varying the distance, I could just sit at the neighboring side, and vary the density. It's very analogous. Yeah? For very dilute gases, I'm deep inside this Polyhole and should see a reduced probability to find another particle nearby. If I increase the density, of course, at some point the probability will grow to 1 for a non-interacting Fermi gas. And how is it for the interacting Fermi gas? Well, we can look at these correlations. We look at single shots of the experiment. We can also blow out one spin state and look at spin up, or blow out one spin state and look at spin down, and try to correlate all these images. The average will give us here this average moment versus radius, which immediately tells us we can immediately obtain the correlations as a function of this local moment, which will be a nice independent way of plotting things independent from theory. If I look at the interferomagnetic correlations, so that's having a spin up on one side, what's the probability to still have a spin up on the other side? It's actually negative. So we see strong interferomagnetic correlations. And when I look at the moment correlation, so the correlation directly of this signal that we observe, then we see a peculiar sign change. And that I should, of course, go into in the next couple of slides. First, the spin correlations do what you expect them to do. At half filling, you have strong interferomagnetic correlations. You find a spin up on one side, there's an enhanced probability to find spin down on the opposite side. But these go smoothly and rather boringly away when you decrease the filling. By the way, the theory here is an excellent agreement without any fits directly coming from theory, because these axes are just directly coming independently from experiment and theory to new data, diagrammatic Monte Carlo and numerical link cluster expansion data, Marcos Rigol, Ehsan Khatami, and Teresa Paiva and Nandini Trivedi. This interferomagnetic signal goes away, of course, as you increase temperature, not surprisingly. Interestingly, the non-interacting Fermi gas also gives you interferomagnetic correlations. That's not surprising, really, because of Pauli blocking again. If you have a spin up on one side, it is just suppressed the probability to find another spin up on the neighboring side. Now here, these are the interesting moment correlations, which show a change from sort of anti-bunching to bunching. So at low filling, we are seeing the physics of fermions. They don't want to be near each other. Fine. The probability is reduced. At high fillings, however, these moments start to bunch, which is an interesting effect, which we can also follow versus temperature. But we can express it more succinctly in terms of this pair correlation function. Here we directly observe this Pauli correlation hole from the textbooks at very low fillings. It's just very unlikely to find another particle next to the first if you have already detected one. And for the high filling case, it's better to look at the anti-moments, the holes in the images, and that their correlations are, of course, the same as the correlations of the moments. And I can plot that G2 function, and it shows this dramatic change from anti-bunching to strong bunching near half filling. But we understand that really well. These are just coming from Dublin hole bunching. The fact that when you have lots of singlets forming in this Fermi Hubbard model, it's very likely that you tunnel over to the next side and form a pair of doublons and holes. So if you take a snapshot of the system, you will often find doublons near holes, and in our parity projected imaging, this would be two holes that are neighboring, and you can have some fun trying to make out how many double holes you find in this image. To summarize, we see the spin and charge correlations for nearest neighbor, but also for beyond nearest neighbor correlations, and provide a spatial map. Instead of for condensed matter experiments looking at Fourier space, we can now look at real space and see the moment correlations and also the interferomagnetic spin correlations, which show the beginning of some sort of checkerboard pattern. But of course, it decays still rather quickly at our temperatures. The correlation length is roughly 2 sides. It is clear that the next step would be to get colder, to study both the repulsive and the attractive Hubbard model is very interesting. One could implant impurities. We have seen beautiful experiments already on that from Marcus Greiner's experiment, shaping potentials and seeing how this Fermi Hubbard model does transport. And maybe if you allow me, I want to give an even more dreamlike outlook by thinking of molecules in these optical lattices, imaging molecules under the quantum gas microscope. We happen to have sodium-potassium ground state molecules in the adjacent lab, so I just need to combine these two experiments. Very simple. Turns out we have sodium also under the microscope, so that's getting there. Turns out these molecules display a wonderful long coherence time on the order of seconds if you look at the nuclear spin coherence. And so they are very interesting for doing all sorts of quantum simulation experiments, but one can even dream and think maybe this is a platform for doing quantum information protocols under this quantum gas microscope. So with that, I would like to end and thank my group, BEC1, on the Fermi surfaces, Fermi 1 on the molecules, and Fermi 2, who have managed to get these amazing images. The people in red are in the audience. Thank you. Thank you for your attention.
Thank you for these beautiful new results. Time is up, but we can have a question.
And with the parity imaging method, how you can detect Dublin hole bunching? Since they, as I understood it, they give the same signal.
Right. That is a crucial. So I can first argue and then maybe find even the graph that I owe you. That would be so great. I won't. But I can just simply give you the story. This is the Dublin hole. Okay, there are three contributions to our moment-moment signal, or the anti-moment signal, if you want. So when we see two holes, what could that mean? It could mean that we have two holes. Great. It could mean that we have two doublons, because they would also show up as two holes. Or it could be that it's a doublon neighboring a hole. Which one is it? So if I have a hole and a hole, these are two fermions. Fermions repel, I will never get anything positive. It will be a negative correlation. If I have doublons and doublons, same thing, because the ups in one and the ups in the other side will repel, and the downs will repel just by Pauli, and you will find negative correlations. So the only way that you can get a positive correlation is a doublon hole pair, and this, in fact, if you don't believe that argument, it actually comes out of the theory, which still, as I said, works at these temperatures. Doublon, hole are always negative. The only positive contribution is coming from doublon hole pairing, and it is coming from this physics that you start forming many of these singlets, and so it becomes just very likely that you catch the system as one of these guys has jumped on top of the other, leaving behind a doublon hole that you can then image.
I think we should now close the session. Let's thank Martin, Hans-Christophe, and Christophe Salomon for their wonderful contributions to this session.